Good morning and good afternoon to all of you. I'll give a talk on design, development, demonstration, and deployment of concentrating solar power technologies, mainly indigenous technologies. Um, as you know that the solar energy can be converted directly into various other renewables and then indirectly various other renewables and directly into solar thermal and photovoltaics. I'm going to concentrate the concentrating technologies on for solar power generation in this talk. You know that for electricity production, power generation, there are two routes from solar energy. One is thermal route, converting solar into heat and subsequently driving a heat engine and connected to the grid or not standalone mode. In contrast to that, there's a photovoltaics which can be connected to the grid. Of course, both of these may need storage if you want to increase the reliability, and also can be integrated with other energy sources, again making it more reliable. A typical thermal power plants looks like this. Is based on heat engine, and generally most prominent heat engine is the Rankine cycle, and Rankine cycle is operated from the heat source, which is supplied by fossil fuels in general. But if you replace fossil fuel by solar energy, then we can call it solar thermal power plant or concentrating solar power plant. And the replacing fossil fuel by sun is a very attractive option with high temperature technologies. And this can be done by these four technologies. These four technologies have reached to the stage of maturity. And of course, some of them have reached to the commercial stage. And this parabolic trough, linear Fresnel reflector, and power tower. And these technologies generally be classified based on the temperature ranges. If the temperature ranges up between 100 and 400 degrees Celsius, they are called medium temperature systems, and any temperature above 400 is referred as a high temperature. Under medium temperature, there are two technologies, Fresnel reflector, parabolic trough, and in high temperature, central tower and parabolic dish. So in this talk, our experience on these technologies, except this tower, central tower, I'm going to give a 4D approach based on Fresnel reflector, parabolic trough, and dish collector system. And what we call it indigenous technology development in India. So it involves 4 Ds, as I mentioned, that design, development, demonstration, and deployment. And of course, we are closely associated with some of these industries. They go to the next level of commercialization. And of course, commercialization and implementation is done. So at IIT Madras, though we are actually involved in solar, thermal, and photovoltaics, but today's talk is mainly on CSP. So we have done a reasonably good amount of works and activities on concentrating solar power, mainly parabolic dish, parabolic trough, and linear Fresnel reflector, of course, also on concentrating photovoltaics. I will go in this. This is our research facilities. These are actually at the initial development. Of course, now we have gone to the almost implementation level. So perhaps all of you know very well these concentrating technologies. Mainly we have dish and parabolic trough, and this is concentrating photovoltaic system. As I mentioned that our approach is 4D approach. So therefore, most of the technologies are almost demonstration scale at the laboratory, so that they can be taken to the field and implemented directly by deploying it. So these are actually, I have shown here two technologies. Mainly one is a point focusing concentrator, the other one is a line focusing concentrator. Point focusing is solar dish, and line focusing is parabolic trough. And apart from that, we have photovoltaics and solar desalination and concentrating photovoltaics and so on. And And if I will go with these three technologies: dish, trough, and a linear frontal reflector. This is our first generation solar dish. Way back about 15 years back, we started on this activity. And this is a three-dimensional parabola, and it is involved to axis tracking and focus with the receiver, and it produces reasonably good temperature ranges of 640 degrees with a 67% efficiency solar to thermal conversion. And in fact, we have come up with various generations of dish. Now, this is actually second generation dish, but we are at now fifth generation 5G dish. The design of these concentrating solar systems are very important for large scale implementation. These designs include essentially optical design, thermal design, and structural design. So I will quickly cover all these designs and ultimately evolving a deployable system. And a parabolic dish, point focusing system which concentrates solar onto the receiver, but receiver needs to be developed such a way that absorb maximum energy. As a part of this, several cavity receivers have been explored, and ultimately modified cavity receiver. See that the modified cavity receiver seems better than the others. And we have done comprehensive optical and structural analysis. And design of a solar dish involves first optical dish, optical analysis that comes from the primary. Better to mute. Go for microphone.
Hi, Safa. I'll
mute everybody. Mute. Can you
Yeah,
put
okay.
your apologies?
Yeah. Now I'll continue. Can you hear me now?
Yes.
Yes. Okay. Very good. Thank you. So the design of a system involves optical analysis, and the optical analysis involves the primary concentrator. Generally, the dish collector is in parabolic shape. So making parabolic, making these mirrors into parabolic shape is very difficult, accurate parabola. So therefore, we generally allow some level of inaccuracies which involve in fuzzy focus. If you have an accurate system, you'll have a point focus, but when you go for some inaccuracies, you'll have a wider image, which may result in a fuzzy image. And but it's required also, because in order to have effective heat transfer, we may need wider focus. We cannot afford to have a point focus for effective heat transfer into working fluid or subsequent processes. And as a part of this, we explored the fuzzy focal image. And first generation dish looks like this. You have concentrated with multi facets, and of course there is some level of fuzziness in this in order to take care of the structural and thermal and optical parameters in this. So, but these dishes dish produce high temperature heat, and the receiver design is very important. The essential feature of the receiver is to absorb maximum amount of reflected radiation with the minimum heat losses. And estimation of heat losses, because since it's a two-axis tracking system, it continuously moves with the sun. So therefore, the receiver also moves along with the dish. So therefore, the receiver orientation and inclinations are different. So therefore, it is subjected to open environment in which we have lot of extreme environmental conditions. especially in India, we have dusty and gusty conditions. And so the geometry, orientation, temperature, and wind speeds and directions are very important. Based on that, we need to do a complete computational analysis of this receiver with the different inclinations here. And then we need to assess how much heat is lost to the environment. Accordingly, we can design the system. We can design these receivers with different aspect ratios and so on. And based on that, we can come up with how the combined heat losses with the geometrical configurations and so on. And then we can find out the overall heat transfer coefficient, which ultimately will get about 76% of the efficiency. And there are heat transfer correlations were developed for this particular type of receivers, and mainly to come up with a non-dimensional parameters. Of course, the fluid needs to be sent into the receiver, and either it can be oil or it can be water. If we circulate water, it will exist 3 different regions, both sensible, evaporation, and superheating region. So therefore, we need to distinguish these regions, and accordingly we need to design this. So you can see that a typical receiver is a volumetric receiver in which the pipe is wound in spherical, spiral as well as helical, and ultimately we'll get this kind of configurations. The input is from the bottom and the output is from the top, and various flow regimes have been considered here. And we can do detailed heat transfer analysis for these in order to optimize the configuration of this. You can see that where the blue is a low temperature region, where this yellowish color is a high temperature region, and red is even further high. So therefore, the flow, how it goes from the top, bottom, and then comes out from the top. So therefore, the flow distribution within the tube is very important because of huge frictional losses or pressure penalty. And based on that, how the flow distribution within the tube and how the phase change happens, because the liquid water is converted into superheated steam in this in order to supply to the power generation. You can see at various cross sections, initially it is completely blue, that means the liquid state, and it moves like this, and finally we get these kind of profiles. There is a two-phase region, and of course finally we'll get superheated steam. And with this we can both optical and thermal analysis, we can make a system at a demonstration scale. But what happens is one dish, if you see that is photographed, this one dish is not enough to go for power generation. So therefore we need to connect such dishes in parallel and series to make a solar field. And when we go for solar field, the single dish design is a different ball game, and an array of solar field is a different ball game. So therefore we need to see that when how the dish will interact with surrounding dishes when in the field. So therefore mainly when we go for two closer locations, then you'll have a shadow of one dish over the other. The shading effect will be there. You can see that if there are two dishes are one in front of the other, then there is a shadow of this. So in order to minimize this shading or shadow, what one can do is we can keep them apart. But when you keep them apart, the land area requirement will become higher. So therefore, we need to optimize the space. Nowadays, the cost of land is also very, very substantial. So therefore, we need to optimize these configurations, mainly in terms of the land utilization. And we have come up with the optimum distance in both east-west direction as well as north-south direction. And if you place a dish, the reference dish is at the center, and it will be surrounded by about 8 dishes in a field. So this one dish, the reference dish, will cast a shadow over all the 8 dishes. So So therefore, we need to space them such a way that they are optimally spaced and with minimum shadow. So we have done a comprehensive analysis. Again, the shadow differs from location to location, and especially we have come up with a field analysis to entire India from 8 degrees north to 35 degrees north. That means it's from low latitude to high latitude of the Indian conditions, and then we came up with a solution. When we implement this in a power plant, power generation, concentrating solar power, the field, you can see that field is connected, and then this is the power plant cycle. And we have done extensive analysis to the entire country, and we have come up with 3 criteria where these power plants are viable, conditionally viable, and unviable with the present technology. Maybe if in future this unviable technology, unviable regions may become viable or even conditionally viable. See, these blue, green color locations are viable with the present technology under present economics, whereas the blue ones are conditionally viable if there is some kind of subsidy or some encouragement from the government. These locations may become viable. But these red locations is very difficult because the solar radiation levels are much lower as compared to the other areas. So therefore, it's very difficult to have a viability in this. But again, these dishes can also be used in order to increase the reliability of the dishes, because you know that solar systems work in daytime, but we have to make them operated throughout the day, 24 hours. So in order to make them operated 24 hours, we need to store some part of the energy, and we can use them in off sunshine hours. In order to do that, we have come up with a new type of receivers for high temperature applications, and in turn we can produce hydrogen and store it in, it can be used for both buffer, extended and seasonal storages. And we have done some simulation studies for hydrogen production. This is the reactor, hydrogen reactor, and which is mounted on the dish, and then you can see these things. And we have come up with a different reactors in order to produce this, and this complete heat transfer and thermal analysis of this. And based on that, you can see that this is the kind of receiver, and this is a multifaceted dish. This is our 4th generation dish, and these are different dishes. One of our industrial associates has developed with our our collaboration. This is a square dish, mainly used for photovoltaic application, concentrating photovoltaic applications. These are all in our lab, and this each one is about close to 30 to 40 kilowatt capacities. And based on that, this is what demonstration, and then we have gone with the deployment with our industrial associates. This is deployed, this 3rd generation dish is deployed in a pharmaceutical industry, and it produces like this. You can see here high concentrated heat, and which is used for process heat applications, and these are their brochures and so on. The next one is the parabolic trough, which is a single axis tracking system, and this can produce about 350 degrees Celsius and 62% efficiency. And again, these are connected parallel and series arrangement in order to produce. And the design, mainly structural and design and thermal design, involves in these 2 types of concentrating solar power, mainly concentrator, support structure and tracking, and receiver. These are the 3 important components. We need to design them in order to make them a concentrating solar power system. So therefore, the performance of the system can be improved by increasing structural stability and thermal capacity and heat storage, reflectivity, and of course absorption of the receiver and concentrating solar flux. Working fluid is also another important thing. So based on this, we can see the parabolic trough collector is this, and which involves a multi-layer reflector coating, and it's a fragile mirror making into this curve shape. Will have other losses, and especially India is a dusty condition and cleaning is a major thing. So therefore, the durability and stability are very important. So therefore, we need to go for effective concentrator. And structural stability is also very important because it works on high windy, gusty conditions, and bonding between this, and the tracking system keeps always the concentrator with the sun. So therefore, single axis tracking system development is also very important in this. And the receiver is an evacuated, it's an heat exchanger, evacuated receiver tube, which involves absorber coating, vacuum, glass to metal seal, and absorptivity stability are very important. So therefore, development of this will be an important issue here. There are several issues related to this, and finally we get this, and then again the receiver design depends on the optical distribution, and the receiver should handle both. It can handle both water as well as thermic fluid. So we have to increase the heat transfer coefficient by improving by inserting some porous medium inside, and we can make the stability of the receiver and we can use it for higher temperatures and higher performances. And typical, I'm not going into details, but the flux distribution is very important at the focal region. And in order to design, because any oversizing or undersizing will result in significant drop in performance. So therefore, this is an optical analysis of this. And based on this, we go with the sizes of the receiver. And if a smaller receiver will have a less absorption, interception of the reflected rays. If you have a bigger receiver, then it will lose heat to the atmosphere. So therefore, the flux distribution in the focal region and getting appropriate concentration ratio is very important. So, so this optical design is very important as far as the receiver design is concerned. Once the optical design is over, we need to go for thermal design in terms of the receiver. We have come up with a wide ranges of receivers and wide configurations, and ultimately optimization has already happened. And then based on this, we have come up with an enhancement factor mainly for improving the performance, and the heat transfer per meter square per meter length and their efficiencies have been found, and ultimately an optimal receiver with porous inserts have been done. And based on that, we go for a complete system analysis. See, we have installed in our rooftop. This is a big parabolic trough. This is a about 5.77 meters, which is used for power generation. This is used for power process heat applications. We are working with various industries, mainly process industries, and this is a mini power plant. It's on a demonstration level. But then when we go for power generation, it has either to be integrated with the heat exchanger field, or we go for direct steam generation. They have their own distinct advantages and limitations, but the most popular ones is this thermic fluid system, but direct steam generation is under development. And based on this, we have developed a 50 megawatt power plant standalone system in a holistic approach that includes energy, exergy, environment, and economic analysis. And we have also studied with conventional solar, conventional coal-based power plants, and how to integrate solar energy, solar collectors with the conventional conventional coal plants. It's a hybrid power plant, and where to inject the steam, whether which feed water heater, and the optimization is happened. The most appropriate injection, steam injection from the solar field is in high pressure feed water heater would be a better option. And this is about solar parabolic trough, and then the another solar concentrating system is the linear Fresnel reflector. This is an inaccurate version of parabolic trough. You can see that the instead of going for a curved mirror, it's a flat mirrors, and these flat mirrors focus the radiation onto the receiver, which is on the top of this, and maybe about few meters away from the field, and you can see the flux distribution here. And again, the receiver design is very important. The receiver design is very important. So then we go for optical analysis, both primary and secondary concentrator modeling, optimization, and error analysis need to be done. And in this, we see that there are different mirrors, and they are oriented differently because all these mirrors need to focus onto the receiver here. So therefore, they have to be tracked independently or integrated manner, and all these rays reflected and focused onto this. So therefore, the optical analysis is very important for this, and then subsequently the receiver design. We have different aperture reflectors and different transmissive. These are optical thermo-optical properties, and based on generally the optical analysis is done on based on the ray tracing model, and all these rays are reflected to the receiver in different directions and then focused onto this receiver. And there is a secondary reflector which concentrates on this receiver tube. And based on this, a comprehensive optical modeling has been done, and then come up with a design of various configurations. And you can see the flux distribution within the receiver tube looks like this. And then with this flux distribution, one need to do heat transfer analysis. You can see with the different orientations and so on. And the wind direction is also plays a major role in when we go for heat transfer analysis. So this is a typical trapezoidal receiver, inverted trapezoidal receiver, in which the tubes are placed here. All the mirrors focus onto this receiver. When we send the fluid from one end, you'll get the superheated steam on the other. And we can even go for up to 500 degrees Celsius with the different conditions. And we have come up with various operating parameters and evolved. This is our prototype system. You see that they are focused onto this receiver here, and this is about 50 kilowatt system. This you can see the receiver. This part you can see here how the flux is concentrated. The accuracy of reflection is very high. You see that this is a perfect line here. So, and the receiver is this, and it involves several heat classes. Then we have also done comprehensive CFD analysis in order to find out the heat classes from various directions, and then found the optimal configuration of this. And this we have implemented in a school in which there is a tri-generation. It's a residential school. This is the field, and it also drives the turbine, and it is used for cooking applications and also for cooling applications like air conditioning. So it's a tri-generation option. Heat, power generation, cooking, and cooling applications, air conditioning applications. And we have again done a comprehensive analysis, energy-exergy, environment economic analysis, and we found where the irreversibilities and inefficiencies are involved, and accordingly we have adjusted the conditions. And these are formulations for various techno-economic analysis. So I'm not going based on this. We can find out what are where the maximum heat losses, minimum heat losses have been estimated, and then accordingly, this is the one which we installed in school for tri-generation, which involves energy storage here also. This is energy storage, molten salt energy storage, and this powers this school, and it produces about 400 degrees with a 50 bar pressure. And the deployment level system is this. This is a system which is a prototype, actually prototype for 1 megawatt system, and you can see superheated steam coming out of this. You can see here, and this is used to drive the turbine. And so this is a prototype, and this is I think our group there. And I will show quickly deployment in 5 minutes. So our industrial associates, can you see this?
Yes.
This new one. Just you can see that slide.
Yes.
Yes. Okay. So this is our industrial associate. It's a imperial kg design. And you can see that the parabolic trough collectors and linear Fresnel. This is the linear Fresnel of our industrial associates location here, and integrated with Abengova parabolic trough in 1 megawatt power plant. And this is our another industrial associate where dish is also dish, linear Fresnel reflector, and parabolic. 3 of them are placed here. And you can see the field here, this is
We can't see that anymore, Professor Reddy.
Huh? Yeah.
Just the heading we can see now, but
You cannot see this.
no.
Oh, that's why I am asking. Oh, sorry.
We can see a slide, but it's just a title.
Oh, some problem is there. 1 minute. You can see now?
Yes.
You can see this, isn't it?
Yeah.
Yeah, I'm sorry. Actually, see, this is 3 technologies you can see here. I'm going back, and parabolic trough, linear Fresnel reflector, and the dish collector. Here, all of them placed here, and you can see the field here. This produces about saturated steam and with the pressure drum and so on. And this can also be integrated with biomass for multi-factor solar desalination. This is located somewhere in the close to our campus. You can see aerial view here. It's a parabolic. This is a linear Fresnel reflector and used for seawater. Bay of Bengal water is taken and produced seawater. This is a typical demonstration deployment in the field. You can see these receivers, and this is a desalination system. This is the collector field, and we have done extensive analysis here. Our industrial associates placed, just I'm clicking through. This is the heat exchanger where multi-fact desalination happens, and these are some of those pictures. Deployment. The water is produced with this. So deployment here. This is the field, and this is another deployment. Here you can see that this is the deployment of these extreme accumulator, and some of these I've shown. So you can see that this is a biggest plant in India. It's a power plant. This one. Another industrial associate is this. Is mainly dish for various process heat applications. You can see how to integrate them in rooftop. The parabolic troughs are placed on the rooftop, and the dish is this, and it can supply required heat. So you can see them. There are some case studies I have shown here as far as the deployment is concerned. These are the parabolic trough collectors which are connected series and roof mounted, and it can also be used for paint sludge drying and pressurized hot water production. And this is a fossil fuel integration hybrid and thermic oil fuel based system for process heat applications. And this is for sludge drying deployment. You can see that various locations they are deployed, and it's also used for cooking applications. The solar dishes are integrated with this cooking kitchen and producing the required food. So I have shown the CSP plants which are first designed, developed, and demonstrated, and of course deployed in various industrial applications. So with this, I will end my talk. I hope I have done within the time. Thank you so much. If you have any questions, you please let me know. Before closing it, I am from India, and I am from IIT Madras, which is southeast located in India, and we are having a big campus of 900 acres, and it's a reserve forest. Some of you must have visited, and these are our friends. You can see them, and this friend is looking at you eagerly for some questions here. So if you have any questions, please let me know. I'll clarify. Thank you very much.
Professor Reddy, thank you very much. Can you hear me? Professor Reddy, thank you very much for your very interesting talk. You've done a lot of work, very impressive, very huge amount of work. So now I ask my colleagues to, they have any questions, if they give
Mustafa,
their
there
name.
are about 5 questions on the chat at the moment.
Maybe you could follow that if on the chat, or maybe they could ask questions, they want to do it this way. Please, colleague, do you have any questions to Professor Reddy? There are a few questions on the chat, Professor Reddy. Can you see them?
Just one.
On the chat box.
Chat.
If you look at chat, there's four questions there.
Chat.
Can I read them out?
Yeah, I cannot see them.
The first question is how important it is to keep the reflectors clean, and how do you achieve this?
Yeah, I think it's very important question. And reflectors, keeping the reflectors clean is very important, and especially when we have dust and extreme weather conditions. We had an experience of our one of the locations. We have observed that if you don't clean for about 10 days or 15 days, the performance has dropped about 25 to 30%. So it's very important. So therefore, the cleaning is generally be done once in a week, and it is water cleaning, water-based cleaning. When in case of small plants, it will be done manually. In case of large scale, it will be done by a spray mechanism with a robo concept.
Okay.
One more question because time.
Okay. One more question. Required area for 5 megawatt solar parabolic dish power plant is how much? And what will be the total price of a 1 megawatt parabolic dish power plant?
For 5 megawatt, the area required will be somewhere to 30 acres, 30 to 35 acres of land, 35 acres. And the cost of the parabolic dish is about 9 crores a megawatt in Indian rupees. I think about 900,000, 9 million pounds.
Okay, thank you. Thank you very much. So one last question. I can see that somebody sent last questions, and you can see from Sadiq.
You want me to read?
You can read it.
Okay, one last question. How reliable are the tracking systems based on your long-term experience?
Tracking systems are very reliable because the accuracy of tracking is very important. Generally, we go with about 0.1 degree of accuracy, and so they are very reliable. But in this tracking system, the 3 important components are there. One is a sensor, a drive, and control mechanism. So they have to be integrated effectively. But with our experience, we could get a high level of accuracies because even the focal distance of 5 mm we could track it. We could up to 5 mm of dispersion can be tracked. So therefore, they are effective.